Nikitas Angelinas from Xyratex. He's going to talk about the network request scheduler. The network request scheduler. Nikitas.
Right. So, how do I use this?
Just to the right is forward.
This backwards, yeah. Right. So I've had a very little sleep tonight and the night before. So I've got loads of slides, and I'm going to go through them quickly. So if something doesn't seem right and you have any questions, you can grab me later. There's a coffee break after this as well, so no problem. So in this presentation, I'm going to give you some NRS background. This is mostly for people who don't know what NRS is. I'm going to describe what tools we used and what sort of results we got for the different NRS policies. I'll talk about policies later on in the presentation. But before that, why should you listen to this, basically? Well, NRS holds the promise of helping in many different things. One of them is helping with either read or write performance across the cluster, either directly or indirectly. Directly would be via either having improved performance in for example, reads. We have a policy that can improve the performance of the file system by arranging requests on a per offset basis. I'll talk more about that later. But it can also do other cool things. For example, it should allow us to do client prioritization depending on client or export, or introduce some QoS semantics at the file system level. So this version of NRS is carried out as a collaborative project between OneCloud and Xyratex. The code is over there. There's the work is all tracked under a Jira ticket in OneCloud Jira, and the reason this hasn't landed yet is, and the code has been sitting there for a while, is that the code has been waiting for some large scale testing. So basically, we need to prove this thing is usable and it has not introduced any performance regressions before we do anything with it. For those of you that don't know what this is, it's a subcomponent in the portal RPC layer that allows us to shuffle and direct the way the order in which bulk IO RPCs are handled. Actually, we can reorder any sort of types of RPCs, but we're probably mostly interested in bulk IO RPCs. And it works on the server, although there may be some thought in there may be some usage scenarios that we can use in the future in which the client is also taking a part in all this. But this is probably early days in the project, so there's probably no point in talking about that further. One of the basic components of the NRS framework is a binary heap that was developed by Eric Barton, I think, if I'm not mistaken. And this allows us to create prioritized queues of RPCs at the server. So the idea is that with current Lustre code, for example, bulk IO RPCs are treated in first in, first out order. It doesn't do anything overly dramatic or smart. And this is what we're trying to change with NRS. So in NRS, for example, you hear the term policies. So we have, you just probably think of policies as different facets of NRS. They work in conjunction with the base NRS framework, and each of them tries to do something different. So for example, you get the FIFO policy, which is just a logical wrapper around current functionality. And you get a bunch of policies that are that do round robin over something, and these policies aim to provide for fairness across the cluster. So, for example, you can handle bulk IO RPCs in a round robin fashion across clients, for example. or you can handle bulk IOR RPCs in a round-robin fashion across OSTs. And the idea is that these policies will give us better fairness and better performance indirectly via making better utilization of file system resources. Then there's some other policies, ORR and TRR, for example. These are the policies I was talking about that aim to exploit relative offsets between requests, and they bundle them together. And this has the promise, at least this has been the idea, that they will, handling the IOs will result in less seek time in the drives. So the drive seeks are a mechanical operation predominantly, and compared to everything else that happens in there, they take a lot of time. So if we can save some of that, we'll hopefully improve read performance. There's also a couple of other policies, client prioritization and QoS. We haven't implemented these yet. Probably the most elaborate policies, something for the future perhaps. So I've talked about this. Just some basic stuff to help you understand with what we're going to be testing in this presentation. So the idea is that all portal RPC services in Lustre servers use the FIFO policy by default. You can enable any of the other policies I mentioned before. And if those policies fail a request, then that request is routed to the FIFO policy. So the FIFO policy acts as a default way and a safe way of handling requests. So you can change the status of which NRS policy is handled, is used in which portal RPC service via LPROCFS, which is what you'd pretty much expect, I guess. So a few words about the benchmarking environment we will be using for this test. So obviously the code has been rebased on the same Git commit as vanilla, just so that we're not seeing any performance ups or downs from any other factors. We're using standard tools mostly for testing, IOR and MD test, also IOs on a clustered mode, and DD-based test script that we put together. So we're using just a single Xyratex box for this. So it's 2 OSSs, 4 OSTs each. Depending on the test, we use from 10 to 128 clients. So depending on the test and also availability, because actually we carried out some testing at the University of Cambridge, but we were sort of cut short for lag. So this presentation has what we currently have, but we will follow up what we have missed in the future. So up to the first test. So the first thing we want to show is that the NRS framework with the FIFO policy has not introduced any unwanted performance regressions, because if it has, we should probably look back to redesigning stuff, or well, not land this, I guess. So for this series of tests, we're using IOR for single shared file and sorry, I haven't slept as I said, or single cell file performance and file per process performance, and also MD test for file and directory operation for metadata testing. So I'll move on with the results here. So as you can see, for 128 and 64 clients, this is the file per process IOR test. There's little to no performance regression. Actually, the small variations you see is probably something that we cannot really directly measure, and there was some ideas by Andreas at some point that we may need a new tool for this, but as I said, these tests are to prove that there are no major performance regressions, nothing significant to work out, to look out for, and also we've done these runs a few times, so these are averages. So obviously, with the more runs you do, the more confidence you can have at the results. There's also the single thread file counterparts of the previous tests. So 128 and 64 clients. Again, you see vanilla read and writes compared to NRS with FIFO, and there are no performance regressions as well. Sort of the same for MD tests. So, so we have here a 128, and also after that a 64 and a 12 client test. Well, basically 12 was all I had in the lab. So, but the reason these have not been put together in a single chart is that I mean, let me show you the next ones. For example, you see for create and unlink, you get different performance, but these separate tests were performed against different rate setups in case you're worrying about that. So again, there's little variation in the 128, for example. I don't think it's something to worry about, but again, I'm not sure if it's enough to tell us that yes, this component is safe to land. But as I said, we will follow up with more extensive testing and talk to the other members of the community in order to come up with a different test plan if they have any different ideas. As again with 12. So that was FIFO testing. So after that, what we can do is look at testing a different policy. So we'll use for the client round robin testing, we'll use CRR-N. So CRR-N, what it does, if you look at the code, for example, it's called CRR2, just in case anybody gets mixed up. So this does client round robin over NIDs. The difference with the previous client round robin policies that the other one does client round robin over exports. But for most intents and purposes, this is probably what you want. So for this, we have put together a script that fires off loads of DD processes at each of X number of clients. So these clients do those operations over there. And the good thing about DD is that you can send it a USR1 signal, and it will tell you how much performance it's been seeing up to an X point in time. So we use that as a basic rudimentary tool to examine the CRR-N policy. And also another thing we're interested in is the standard deviation seen at each client. I'll explain why later. But before we get to see the test results from that test, here's the purpose of this slide is to make sure, to prove to you guys that what we are testing is what we think we're testing. So this is just a debug log from using that policy on the server. So for example, you can see the NIDs there on one of the tabs in the middle. So I've sort of color-coded the tabs on the right. So if we're doing this test with 14 clients, for example, if we take the first client I've color-coded, which is 1.23, if you have the courage of counting, it's 14 up to the other occurrence of 123, and it's pretty much the same for any of these entries you take for as an example. If you see small variations, it means that at that point, at the point that the particular I/O came in, the other client that was meant to be there did not have a pending request at the time. So this is a side effect of the way the binary heap works for these policies. So the idea that Eric had with the binary heap is that requests come in and they get assigned a priority at arrival time. So, but this sort of has the side effect that you may not get completely perfect distribution, but I mean, the alternative would be to not use a binary heap and use something that's a lot less scalable, like keep requests in a linked list or something like that, which is not what you want to do with, let's say, having 10 million requests, and you want to, go through a list of 10 million requests at the server. That would be madness. So, but another thing to keep in mind is that these results are only with 14 clients. So if you have a large cluster, that's going to be a lot more loaded. The distribution you'll get will be a lot better because you'd have a lot more pending requests. So, well, that's in the average case at least. So on with the test results. So, so with blue, we've highlighted the vanilla code. With green, there's CRR-N. So we're doing a write test from 10 clients. They each fire up 10 DD processes and do a write from dev0 onto a different directory at the file system. And each of them writes a different file on that directory. So, so you see the blue line, for example, you see client 2 is experiencing less performance within reasonable limits though. Client 5, for example, is again a bit higher. Client 7 had a problem at the time. I don't know what. I didn't even look for it, but it was a fortunate occurrence actually, because it helps us out understand what CRR-N can do for us. So with CRR-N, which is shown with using the green tabs, you can see that the standard deviation has gone way down. So CRR-N has evened out all the writes. It's helped out client 2. It's helped out client 7 as well. So this is something probably people will want. It should be able to give predictable performance, right? So this is probably something to look out for and run some more extensive testing in the future. So after this, we have the same DD write test, but with out of those 10 clients, 9 clients have 11 DD processes, and client 4 has been intentionally left with just 1 process. This test is to showcase a different use case. I'll explain more in a bit. So with vanilla, for example, you see the standard deviation with CRR-N against vanilla has dropped dramatically again, same as in the previous slide. So you see the same evening effect here in this use case as well. And the bandwidth for client 4 has also increased a bit. It hasn't gone up to the levels of other clients, but this is probably something you would expect because it also only has 1 DD process. But the client has been, the write throughput has been helped dramatically, you'd have to say. It's more than a tripling of the performance. So this goes to demonstrate that a single client that's producing very few RPCs, either because the application it's running just produces very few RPCs, or because it's experiencing some other sort of problem. And at the same time, on your cluster, you have other clients that are imposing a really heavy I/O load on the cluster. So in this case, the CRR-N policy should help the one process client, which could be something else in real life, to get a bit higher bandwidth. So, I think this should have some use cases as well. A side effect of CRR-N may be increased throughput. If you see on the previous slide, the throughput is a bit higher, but I wouldn't really trust this test for this particular thing, because I mean there's this variation in testing that you obviously get, but it may well be possible that you will see a performance increase when the clients are actually doing some processing. So I mean, here we have a DD processes, which I presume really do I/O for most of their lifetime. Whilst in a real life scenario, you may have applications that actually do some processing and are waiting for I/O, and at the same time that they're waiting for I/O, they could be doing something a lot better. So they could really benefit from that I/O happening sooner. So you may get increased performance. So that's DD write. Then there's a series of DD read tests, which are not at all spectacular, as were probably the previous ones, where where you saw some dramatic differences when you use the CRR-N policy. Here we see even a worsening of standard deviation and throughput, and this is repeatable against many runs. I'm not sure why this is so. I probably attribute it to the difference in the nature of read operations as to writes, i.e. synchronous versus asynchronous. But this is definitely something to look out for, and re-examine, what the environment was for the testing. Then there's another DD read test, again with the previous configuration of 9 clients with 11 processes and another client left with 1. And you see again the same behavior as with the previous test with 10 DD processes per client. So that falls under the same category. I wouldn't put much emphasis, on the improvement of client 3's bandwidth, although it is something that you would expect to see, definitely. And it will probably be very interesting to see how this policy will behave in a lot larger scale scenarios. But this is a simple test that can show us what we can expect and what we can hope for from these policies. After this, we have an IOR file per process test between vanilla and this CRR-N policy, and again, you don't see any major performance regressions. And again, the same for single shared file performance. So these 2 slides are to show that in case we decided that the NRS framework with the FIFO policy is landable, we could also land the CRR-N policy and with some degree of confidence, and also and this would allow us to get feedback from real life clusters, which would be a lot more interesting, definitely. So what we saw in this test is that CRR-N seems to even things out a lot for write performance, but it has a negative effect on read performance test results. I guess in the worst case, reads could be routed through the FIFO policy, either intentionally or unintentionally, failing those requests. For example, CRR-N could say, "Oh, this is a read request. I'm not going to handle it." So this may add a bit more overhead, but it's looking at the. I think looking at the opcode in NRS, maybe something that should be put on the framework and not be left on the policies, because ORR and TRR, the next policies we're going to look at, also use this. And then this would also mean reworking some of the portal RPC layer functionality as well. But anything is possible. I know Liang has been talking about reworking the locking as well in portal RPC if we land this. So that's a possibility. An important thing that I have pointed out is that the future testing task is to see if these results scale at something with 100 or so clients.
We've got about 5 minutes.
5 minutes.
19 more slides.
No problem.
All right.
So we've finished with these policies. Let's have a quick look at ORR and TRR policies. So what ORR does is it only handles read requests. There's also an option to handle write requests, but let's not worry about that. It was only put in as a test. So ORR, what it does is that it will take a bunch of requests and reorder them in a manner that will be more favorable for the backend file system, in order to minimize seek operations that I mentioned earlier. TRR, at least this version of TRR, and not the version that has been mentioned on the NRS HLD thread in Lustre Devel, also does a similar thing, but it doesn't look at the object ID at all. Because I thought it would probably be favorable for a policy to mix requests from different objects, because still they may be contiguous in physical disk offsets. So that's what's been implemented here. The other version of TRR was to just do TRR at a higher level with an RR quantum of 1, but I'll talk about that later. It's something of that's to be part of the future tasks in an NRS framework evolution. So I guess again the same sort of slides that we had for CRR-N, and this is with a round robin quantum of 8. The fizz there in the parentheses shows that tells us that we're doing request ordering on physical disk offsets. So physical disk offsets are we get the logical disk offsets, then perform a FIMAP call, calculate the physical offsets for the requests, and use those for the ordering. So again, you can use the color coding there and see that pretty much the grouping is 8 by 8. And also there's a bit of a variation for the same reasons I have explained before, i.e. there wasn't an RPC at the time. This particular one, the one with the purple color at the end, is an artifact of, again, one of the reasons I have explained, i.e. A request came in for a previous object. But this really shows us that these policies could do with an upgrade, a reference count that would just restart the groupings. Then there's TRR, again the same. I'm going to leave these for people to look up in the future, I guess. So with ORR and TRR policy tests, we're going to do some SSF and file per process testing. I'll move on to the results. I think I don't have a lot of time. So you see here a graph of IOR file per process read. And you can actually see that TRR physical has been of the most help in improving performance, which is what you would expect, what the theory tells us. Mixing requests of from different objects using physical offsets would provide us with the best performance. And another thing you also see is that for both ORR and TRR, physical offset ordering improves performance more than logical offset ordering. So that again backs the theory that if you reorder requests on a physical disk offset rather than on a logical disk offset, you'll get better performance, unless doing the FIMAP calls, etc., adds more overhead than what it gives back to you. An important thing to note about these tests is that they've been performed with only 14 clients, and because reads produce less RPCs, I've lowered the OSTIO threads on the servers to 128, but I also have some 512 results later that I will show if I have enough time. About a minute. So here's an SSF test, in which case ORR and TRR policies have not helped at all. But again, you see the physical and logical offset ordering discrepancy that favors physical offset ordering. This is with 8 clients. You see ORR is of benefit. Again, these results are to be, probably rechecked at a higher scale, but I think they're promising at what they do. This is a case where ORR and TRR show some really bad performance. I think it may be down to how IOR creates threads and schedules requests, but it's definitely something to look at in the future. This is an IOZone test. Again, you see TRR physical being of a lot of help. And another thing you also see is that all these policies have this is IOZone output, by the way, have reduced the minimum and maximum, have brought the minimum and maximum values together for each of the clients. So I expect if you run the DD read test, you will see again the same results. If you run it with these policies and not CRR-N, as you did with CRR-N, which lowered the standard deviation. I just haven't measured that yet. So this is another example with large read ahead where we were using 512 threads, which is the default. But we used a large read ahead to actually generate more RPCs to be able to test this in the lab. And you see again the same pattern for IOR FIFO process and for IOR SSF test as well. So this sort of shows us that these results should hopefully scale. This is another slide that shows us that the performance for TRR has topped at the 512 RR quantum number, and this is probably something that will vary with workloads. But again, it's early days in the project to say anything with definite sureness. Some notes is that a TRR and ORR may help in lots of different scenarios, and they may be beneficial to some scenarios, or they may be beneficial to a generic workload. And what I mentioned before about TRR is that the original idea was to use it in a multi-layered NRS framework. So you would have TRR at a higher level. It will distribute RPCs against different OSTs, and then you would have ORR, or perhaps another level of TRR inside each OST. But this is something for the future again. I'll just take an extra minute. No?
You don't have a minute. You're
Okay.
2 minutes over.
Okay. So yeah, I'm not going to go through the test results summary. I'm sure you got all of that. Future tasks are to decide whether the NRS framework is landable now, or whether we should come up with a new task plan to carry out. And there's a whole bunch of other stuff that we should do in the future. But again, as I said, it's early days. Thank you.
Thank you, Nikitas.
Thank you.
If you guys have questions.